We'll wait for a few minutes for others to join. All right, welcome everyone to the week 9 of the tutorial session of thermodynamics. So in our previous tutorial, we have finished up with a lot of questions, and we have finished with the second law of thermodynamics as well. And today we'll start with the concept of available energy and unavailable energy. Okay, so let me share my screen so that we can start. I hope my screen is visible. Yeah, now it's visible. Great. Okay, so let me write the topic. Okay, videos also. Cool. Okay. So the topic is available energy. And unavailable energy. So what is available energy basically? So available energy is first of all defined for a cycle. Okay, and it is a maximum possible work that can be executed in a cycle or extracted from a cycle with a certain heat input. Okay, so it's always for a cycle and how much amount of maximum work you can extract out of that. Okay, and unavailable energy is the minimum possible heat that has been rejected to the sink. Okay, so let me write. It is maximum possible work that can be extracted in a cycle with certain heat input in a cycle. Okay, it's the maximum possible work in a cycle. Okay, what is unavailable energy? So it is the minimum possible heat that has been rejected to sink. So it is minimum possible heat rejected to sink. Okay. So if we say work max, when you are obtaining from a cycle, the net work maximum is the available energy, and what amount of minimum amount of heat you reject to the sink is the unavailable energy. Okay. So suppose if you have a cycle like this is at temperature T1, this is an engine E. It's not a reversible, I'm just saying it's an engine E. Okay. So this is T2. Okay. So what is the maximum work you can obtain from it? Okay. This is Q1. This is Q2. So available energy is basically maximum work you can obtain from an engine or a cycle, and unavailable energy is Q2 to be minimum. Okay, minimum heat rejection. Okay, so for maximum work to obtain, if you say heat supplied Q1 is equal to work maximum plus Q2, so work maximum is Q1 minus Q2 when it is minimum. So lesser the heat rejection, more the net work maximum you obtain. Okay, lesser the heat rejection, more amount of maximum work you obtain. You don't want your heat to be wasted to the ambient or whatever same temperature it's maintained. Okay. So if it's a reversible engine or a Carnot engine, for reversible engine or Carnot engine, we have seen so far that maximum efficiency can be written as maximum or reversible can be written as 1 minus Q rejected to that of Q supplied. Okay, Q rejected to that of Q supplied. Or you can say 1 minus T at lower to that of T of higher. Okay, T of lower to T of higher. So what we can say, what can we do here is that to increase the efficiency There are two ways. First way is you supply heat at a higher temperature. Okay. So if this temperature is high, then overall this is low. So efficiency eventually increases. So this overall increases, and because of that, efficiency increases. I'll write that. So that's a mathematical point of view. I'll explain the physical point of view of that as well. The first case is T higher is at higher temperature and T lower is constant. Okay, T lower is constant. So this you can say that efficiency is 1 minus T lower by T higher. So you can say the efficiency will eventually increase. So efficiency will increase. T higher increases, this ratio decreases and efficiency increases. Okay. So that means heat must be supplied at a maximum temperature. Heat is supplied at maximum temperature. Okay. Another way can be if you do reduce the lower temperature. Second case, that is T lower is reduced and T higher is kept constant. Okay, so this implies efficiency is 1 minus T lower by T higher. So that means this value decreases. So overall this ratio decreases. So efficiency increases. So the point to say here is that heat to reject must be rejected at a minimum or a lowest possible temperature. Okay. Therefore, heat is rejected at minimum temperature. Okay. So there are two possible ways to increase the efficiency. One is you supply heat at a higher temperature. Another is you reject the heat at a lower temperature. Okay. So what does it actually means? Okay. So when you supply heat at a higher temperature, what can be the maximum possible temperature to think is? You cannot go beyond the maximum metallurgical limit of the blades which are in the turbine. Okay, so if it's working at a in the power plant is there. Okay, so there are turbines which are rotating. You cannot supply heat maximum than the bearing capacity of the blades, material of that blades. Otherwise, the blades will melt out. So you have to provide the heat such that your temperature of the blade melting, it should not reach the melting point temperature of the plate. Okay, they should not melt down. Okay, and supplying the heat, rejecting the heat at lower temperature means whenever you are in practically also in practical power plants also, if you see the heat is, this is suppose T2. Okay, the rejection, but let us say this is T naught. Okay, this is T naught value, that is ambient temperature. We are rejecting the heat at ambient temperature, but in practical scenario it is rejected at much lower temperature than the T naught. Okay, than the power plant ambient temperature in the power plants. Okay, so that we reuse this heat back. Okay, to increase the efficiency, so that this heat is again reused and to increase the efficiency, and it is rejected at a very lower temperature, so that Q2 in the environment at a higher heat should not be rejected. It should be brought to a very lower value of a heat rejection at a lower temperatures. But what happens when you are lowering down the temperature? If you remember a TS plot, temperature entropy plot. So it's a plot like this. If you see, okay, so this is a TS plot. So when you go lowering the temperature, so suppose your earlier heat rejection was at this temperature, then you reduce to this, then you reduce to this or this. Suppose you go further down, okay, like till here, okay. So what happens? The water content. So if you know what is this kind of curve is there, okay, superheated region, okay, and liquid region and vapor region, that kind of curve is there. So what happens? The water content get increased, okay. Because of that, the steam gets heavier and heavier. The dryness fraction reduces. So what happens? The steam gets heavier and it impacts the blades at a much pressure, higher pressure compared to a superheated steam region. Compared to this superheated region, the steam in this region will be of more having a more moisture content and it will impact more. And blades being a ductile material, they will they can have an ability that they can break off. Okay, so with a higher pressure at such a high speeds working, that's a possibility that blades can break off. So we have to make a compromise in such a way that between any of this region, we can afford that we can take the temperature to a lower temperature than the ambient, okay? But in such a way that only one or two blades get damaged, such that their cost can be covered because you are getting a more efficiency out of that power plant, more efficiency because of lowering down the temperature. So the cost in rupees is more because of the higher efficiency and loss is less. So that it is being a more optimized situation with a more profit compared to just a loss of one or two plates in a practical scenario. Okay. Also, when you take down the temperature to a lower temperature, what happens? Air also gets leaked inside the condenser unit. In the condenser unit, because you are taking from the ambient condition to a lower conditions than the ambient. So that means you are creating a vacuum inside that tube. There is a draft tube if you have studied in your power plant subject. So what happens? You are taking below the gauge pressure scenario. Okay. So if it's going below the ambient pressure, then the air from the outside will also come inside the tube, draft tube. Okay. You cannot take, so you have to make an optimization in such a way, that's engineering, that you have to make an optimization that you cannot take then the less than the very less than the ambient conditions with respect to pressure as well as temperature, so that you have a maximum efficiency as well as a minimum material damage. Okay, so that the cost is beared in the you can say uh, with respect to that of a higher profit with efficiency compared to a lesser damage cost. Okay, I hope it's clear. So in the whole, that was a physical aspect of looking this thing apart from the oh, mathematical concept. So mathematically, we say that if to increase efficiency, we need to have a heat supplied at a higher temperature, not than the metallurgical temperature limits of the blades. As well as you cannot provide the, you can provide the heat at a lower temperature so that efficiency increases. Heat reject at the lower temperature, not supplied at lower temperature. You reject at lower temperature so that your efficiency is higher. So you can either, so there are two things that you supply the heat at a higher temperature, we can supply the heat at a higher temperature and reject at a lower temperature. Okay, all right. So if you see the TS plot once again, so this is temperature entropy plot for a Carnot engine. We have seen it. Okay, again making. Okay. So this is a temperature T naught condition, and this is a temperature T1 condition. Suppose. Okay, so you supply heat at Q1 of heat you supplied, and you reject the heat to the ambient Q naught. Okay, suppose, and this is the entropy change. All right, this is your entropy change. So what can you say? What is the amount of heat supplied? Q1 is T delta S. So heat supplied Q1 is T1 delta S. Yeah. Any doubts? Abhi, do you have any doubts? All right. Okay. So heat supplies is Q1, that is T1 delta S. And this delta S entropy change can be written as Q1 by T1. Q1 by T1. All right. Entropy change is Q1 by T1. So area under the TS plots gives you the heat supplied. Okay. Heat interaction basically. So efficiency is nothing but 1 minus T naught, that is a lower temperature, to that of T1 supply temperature. And it is work maximum to that of Q1. Work maximum to that of Q1. So I can write it down. This is a temperature T naught, equivalent temperature T naught, that is ambient condition. Okay, ambient condition. So I'm rejecting the heat for now at an ambient condition. So efficiency is 1 minus T lower, that is T ambient, to that of T1, and that is work maximum by Q1. Okay. So if you just see from here, so work maximum can be written as heat supplied into 1 minus T naught by T1. 1 minus T naught by T1. If you open it up, Q1 minus T naught into Q1 by T1. Q1 by T. So that is your work maximum. So what you can say that Q1 by T1 is basically delta S from here. Q1 by T1 is delta S. Okay. So Q1 by, it can be written as Q1 minus T naught delta S. So that is your work maximum. And this can be written as available energy, because work maximum is your available energy is equal to Q1 minus unavailable energy. That is minimum possible heat rejection. Okay, minimum possible heat rejection at a minimum possible temperature. So you can take this T naught to a much lower temperature than the ambient as well. Okay, so high, you want available energy to be higher and unavailable energy to be lower. So that you get a sim efficiency. Okay, any doubts still here to anyone? I hope it is pretty clear. Okay. So available energy is a maximum possible work that you can extract in a cycle, and unavailable energy is minimum heat rejection you can do at a to the sink. Okay. And for a maximum efficiency, there are two ways. One way is you can supply heat at a higher temperature or reject at a lower temperature. Okay, I'll give a question to solve. Pretty simple question. 1000 kilojoule of heat is supplied to a reversible heat engine from a source maintained at 327 degrees Celsius, and sink temperature is 27 degrees Celsius. Okay. Then you need to calculate available energy and unavailable energy. Then calculate available and unavailable energy. Okay, take your time. It's a very pretty simple question. All right, I think most of you have done. Let us discuss now. It's a pretty simple question it is. So it is said that you are supplying a heat to a reversible heat engine at 327 degrees Celsius and you're rejecting the heat at 27 degrees Celsius. You need to calculate available and unavailable energy, basically maximum work and minimum possible heat rejection. So let us again draw this. So there is a reversible engine. So heat is applied at 327, that is plus 273, 600 kelvins. So that is 600 kelvins of heat is applied. Okay. And heat is rejected at 27, that is 300 kelvins. So you need to have work maximum. This is applied Q1 at 1000 kilojoules. And you don't know what is heat rejected. Okay, you don't know that. So you know that it's a reversible engine, so basically a Carnot engine. So maximum efficiency can be written as or reversible 1 minus T lower by T higher. And that is nothing but your work maximum to that of Q supplied. So that is 1 minus what is T lower 300, what is T higher 600. Work maximum you don't know, that is available energy, and heat supplies at 1000. So this is 1 minus 1 by 2, that is 0.5 into 1000, that is work maximum. Okay, so work maximum comes out to be work maximum or reverse available energy. So you can say available is equal to work maximum is equal to 500 kilojoules. Okay, and now you know that whatever you supply heat is in the form of maximum work plus heat rejected, that is your unavailable energy. So heat supplied is 1000, maximum work you have got 500 Q2. So therefore unavailable energy that is Q2 minimum possible heat rejection is equal to 1000 minus 500, that is 500 kilojoules. It's a 50% efficient engine. So both efficiency, unavailable energy and available energy are same. All right, pretty simple question. Nothing to worry about. Now let's come to a very important topic of loss of available energy when heat is transferred through a finite temperature difference. Okay. Loss of available energy when same heat is transferred through finite temperature difference. All right, let us discuss. So there are two cases. You first of all you are finding out what is the loss in the available energy when you are supplying the same heat at a finite temperature difference. So there are two cases. First is same heat is rejected and variable heat is supplied. Okay. Another one case is same heat is rejected and variable heat is supplied. Another will be same heat is supplied and variable heat is rejected. So one case is when you are applying same heat and rejecting at different temperature. Another is when you are rejecting at different temperature and supplying at same. Okay. First of all, what is efficiency? Efficiency is nothing but output to that of input. Whatever output you got for whatever input you supply. What is the output? Your output is always work net work you are getting out. And what is heat supply, input? That is your heat supplied. So as per the first law, work in a cycle, net work done is equal to net heat supplied. So that is Q net is equal upon Q supplied. What is Q net? That is our work net is heat supplied minus heat rejected. So that is heat supplied minus heat rejected by heat supplied. So you can write efficiency as 1 minus Q rejected by Q supplied. General way. Okay. So case 1. You say same heat rejected and variable heat is supplied. Okay. So let us make a TS plot first of all. Temperature entropy plot. Okay. So what do I mean from here is that you are rejecting the same heat. There is one case. Suppose there are two power plants with you. Okay. One is power plant A, one is power plant B. Okay. In one power plant, you are both the power plants, you are rejecting the heat at same temperature. Same heat you are rejecting. Okay. So suppose this is a T0 temperature where you are rejecting. Okay. So the rejected heat is suppose Q0. Okay. Q0 is the rejected. So both the power plants have same heat rejection happening. Okay. Now there is a scenario where one case is that there is a higher temperature, there is a lower temperature, T2. Okay. So you are supplying heat at variable heat is supplied. Okay. Through a finite temperature difference. So one case the heat is supplied Q1, at another it is Q2. At another temperature it's Q2. So one power plant is operating between the temperature limits of T1 and T0, and another power plant is operating between the temperature limits of T2 and T0. Okay. So rejection is same, supply of heaters are different. Okay. Different at different temperatures, Q1 and Q2. Okay. Now we have to find out that what will happen eventually. We have written one statement before in our notes right now. We'll see what happens now. So that means Q supplied, Q rejected is constant, and Q supplied can vary. Okay, so Q supplied has two things. Either it is Q1 case or it is Q2 case. Okay, we know that efficiency is 1 minus Q rejected by Q supplied. Just now we have seen. So to increase the efficiency, we should, because Q rejected is same for both the power plants. This numerator is same. Only varying thing is Q supplied. Okay. So to increase the efficiency, we need to increase QS. Heat supplied should be higher. Heat supplied should be higher. If heat supplied is higher, then overall this ratio is lower and efficiency increases. So what is heat supplied Q1? Q1 is T1 delta S. Okay. Entropy change is same for both the cases. Entropy change is same for both the cases. All right. Entropy change is same, delta S. And Q2 is T2 delta S. Okay. Since T1 is greater than T2, we can see we are supplying Q1 at a higher temperature T1 and we are supplying Q2 at a lower temperature T2. Okay, so one power plant is operating at a higher temperature. Since T1 is greater than T2, so product of T1 delta S is greater than T2 delta S. So that means heat supplied is Q1 is greater than Q2. So when you're supplying heat at a higher temperature, your efficiency eventually increases. We have seen this before as well. So you should supply the heat at a higher temperature. That was the first case we had. For a same heat rejection, both the power plants are working at the same heat rejection, but at different heat supplied at different temperatures. Okay, so there is a finite temperature difference. There's a finite temperature difference between the heat supplied. So there is a concept which we are understanding, that is loss of available energy when same heat is transferred through the finite temperature difference. Through a finite temperature difference. So there is a finite temperature difference of T1 and T2 if you T1 and T naught for the first case and a T2 and T naught for the second case. Okay. So first power plant is operating between T1 and T naught. Another power plant is operating between T2 and T naught through a finite temperature difference. So you see that if you supply the heat at a higher temperature for the same heat rejection, the efficiency is higher. Okay. Efficiency is higher. All right. So Q1, power plant 1 is much efficient than power plant 2. Okay, from this. Okay. So we can say that, therefore, heat must be supplied at higher temperature. So interesting. Or from apart from power plant, you can take an example that you have two bikes. Okay. So if you are rejecting from the silencer the same amount of heat, okay, but different amount of fuel you are putting in, petrol, gas, whatever you are putting in both the bikes. Okay. Both are same bike, same brand, but different amount of fuel you are putting in. Okay. Higher the amount of fuel you put, okay, the higher amount of kilometer it will run. That's the scenario. It's more efficient. So it's a very simple thing. If you put higher fuel, higher heat supplied, your efficiency will be higher. But this is not much of an engineering thing. Using extra resources will eventually give you extra mileage. Okay. But with a limited amount of resources and limited amount of wasteness, how you can get maximum efficiency. That's engineering. Okay. That means if you put same amount of petrol in both the bikes and reduce the heat rejection out of the bike from the silencer, that means your unavailable energy heat rejection is less and heat supplied is same for both the bikes. So how you can increase the efficiency? Okay, you can increase the work max. That's the scenario, that you want to have a maximum amount of work with the minimum possible heat rejection. You want to have maximum available, more of available energy with a less of unavailable energy. So that's an engineering concept. So here is a case two. Case two. It says that same heat is supplied and variable heat is rejected. Okay. What do I mean by variable heat rejection? Less amount of fuel I want to waste in the environment. Burning of the exhaust should have in the environment should be there. Okay. And for the same amount of petrol. Or suppose there are two power plants, you provide same amount of heat in both the power plants, same amount of coal amount is there. You have 1 kg, 10 kg of coal or 1 ton of coal for power plant A, 1 ton of coal for power plant B. You put same amount of heat, same amount of supply, but you change the rejection. Okay. So how you can do that? How you can do that? Let's see. You are varying the rejections, Q rejections. Okay, so that you are having maximum amount of work obtained. So first case, let's draw a TS plot. TS. It's a very good concept right now, what I'm gonna teach. So this is temperature T1. This is temperature T0. Okay, ambient temperature, T0 is there. You are supplying heat Q1 here. You are supplying heat Q1 here. And you are ejecting some heat Q0. Yeah. Okay. There is one power plant which is operating between T1 and T0. Okay. There's another power plant. Which is operating at T2 and T0. One power plant is operating between T1 and T0, finite temperature difference T1, T0, and another power plant is operating between T2 and T0. But heat supplied is same for both the cases. So Q2 is supplied, but which is eventually equal to Q1. Okay, both the heat supplied are same. Both the heat supplied are same. Okay, carefully understand that. So this scenario is that heat supplied is constant, and heat rejection can vary. Okay. Can increase or decrease. Suppose you increase or decrease, whatever. So if Q is supplied is constant and Q rejected increases, so efficiency is 1 minus Q rejected by Q supplied. So if Q rejected, suppose I want Q rejected to decrease. I want to decrease. So if I decrease the Q rejected, so my efficiency will eventually increase. Okay, in that scenario. Or if I increase the Q rejected, my efficiency will decrease. But in engineering perspective, I want a higher efficiency. So I want rejection to be much lesser. Okay. So what can we do? We have a first power plant which is operating at Q1, which is written as T1 delta S1. Okay. So this is delta S1. This is delta S1. Just focus on the white curve for the white box, no blue box. This is your delta S1. Now I am saying that Q2 should be equal to Q1. But Q is basically a product of T and S. Q is a product of T and S. Temperature is different. Other power plant is operating at a temperature T2. So to maintain the same amount of heat, your entropy delta S should be higher. Okay. So to maintain the product, if T1, right, since T1 is equal to, or T1 is greater than T2. Okay. And for same amount of heat, Q2 and Q1. And since T1 is 2 and Q is the product of T delta S. So for to maintain Q2 is equal to Q1, for Q2 is equal to Q1, this implies your delta S of 2 should be greater than delta S of 1. Am I right? Am I right? So Q2 is T2 delta S of 2. So for Q2 equal to Q1, delta S of 2 should be greater than delta S of 1. That means my another power plant is now operating between T2 and T0, but with a higher delta S. So suppose my delta is now, suppose a higher delta S, delta S2. Okay, that means now my entropy has increased from this to this. Now my rectangle is from this to this kind of scenario. Okay. Now this is my rectangle of the other power plant operating. Are you getting my point? So my entropy has increased. That means my heat rejection has also increased. My heat rejection is increased. Earlier heat rejection was T naught delta S1. Now heat rejection is T naught delta S2. All right. So that means Q rejection. Earlier my temperature limits were from here to here. Now my temperature limits are from between blue. So there are two different power plants are there. One is from T1 T0, another is from T2 T0, but with a higher entropy. Okay, so as to maintain your same heat supplied. So as to maintain your same heat supplied. So you can say that, therefore, heat rejection QR is nothing but your Q naught, which is for T naught delta S Q1 at T1. That is, or I should write like this, which is nothing but Q naught, which is nothing but T naught delta S1 for Q1 at T1 and T naught delta S2 for another power plant, that is Q2 at T2. Or I can write like this with a blue curve so that you T naught delta S2 for Q2 at T2. All right. This is another power. So two another power plants are working. So heat rejected you have increased because to maintain the same heat supplied. Okay. You have to increase the heat rejection because it is at lower temperature. Q2 is supplied at a lower temperature, but it is same as Q1. So to maintain the product of T delta S, the entropy of 2 should be higher, so that T naught delta S product should be same. That is Q1 is equal to Q2. All right. For that, your rejection will also increase. That is T naught delta S2. T naught delta S2. So if Q rejected has increased, so you can say that this implies, you can say that since delta S of 2 is greater than delta S of 1, so you say that T naught of delta S of 2 is greater than T naught of delta S of 1. That means Q rejection in the second case is greater than Q rejection in the first case. Is it right? So you say that since efficiency 1 minus Q rejection upon Q supplied. So if Q rejection is increased, then efficiency. Therefore, efficiency of 2 is less than efficiency of 1. Okay, efficiency of 1. So first power plant has much higher efficient than the second power plant. Okay, and efficiency is nothing but work max to that of Q supplied of 2 is less than work max of Q supplied of 1. Since Q supplied are same, since Q1 is equal to Q2, that is this and this cancels off. So you can say work max of 2 is less than work max of 1. Okay, that means your available energy of 2 is less than the available energy of 1. This implies, because work max is nothing but your available energy, available energy of 2 is less than available energy of 1. So your first power plant is producing more efficient, having much amount of available energy. Okay. more amount of available energy. And you have to find out loss in the available energy. What is the loss in the available energy? And what is the loss in available energy? Is basically increase in the unavailable energy. Is basically the increase in unavailable energy. So increase in unavailable energy, therefore increase in unavailable energy is nothing but T naught. If you see from the graph as well, earlier your available energy, uh, unavailable energy was T naught because it's a minimum possible heat rejection. So for the power plant 1, what was available energy? Unavailable energy, that is T naught delta S1. And in the second case, second power plant, it is T naught delta S2. So that means this region is your increase in the unavailable energy. Okay, so outer region minus inner region. Outer region minus inner region is your increase in the unavailable energy. So that is nothing but for a same T naught temperature rejection T naught into delta of S2 minus delta of S1. This is your increase in unavailable energy. Okay, or you can say loss in available energy, or you can say loss in available. So Q1 was T1 delta S1. Okay, so this implies delta S1 is Q1 by T1, and Q2 is T2 delta S1, S2, sorry. And both the heats supplied are same. But what is delta S2 from here? Q2 by T2. And Q1 and T1, Q1 and Q2 are same. Okay. Now use these two equations in here. So put this delta S1 and delta S2 in here. So therefore, increase in unavailable energy or decrease in available energy is nothing but T naught Q2 by T2 minus Q1 by T1. And since Q heat supplied is same, our case is that you supplied same amount of heat. You can write it like this: T naught into Q1, T1 taking the LCM, T1 minus T2 by T1. And this is very important expression. Very, very important expression. This is your increase in unavailable energy or loss of available energy. So that is why you reheat in the boiler or reheat, okay, from T2 to T1. That's why we reheat in the boiler so that your heat supplied should be at a higher temperature always. So from here also we are getting an evidence that if you supplied even a same amount of petrol you are supplying, it should be supplied at a higher temperature. Okay, so that you have a higher efficiency. So in both the power plants, power plant 1 and power plant 2, heat supplied was same, but were at different temperatures. So if you supply at a higher temperature, then you are having higher efficiency. That's why we reheat again so that our temperature should be always maintained at T1. Reheat through the exhaust. Okay, we don't waste our rejected heat. And that was the scenario we discussed, the physical meaning when I explained before. Okay, the two cases for efficiencies. All right. So that means there were two bikes, both have same amount of petrol, okay, or the fuel. Same amount of fuel has been provided, but you are rejecting less amount of heat from the first bike and rejecting more amount of heat from the second bike. Okay, that means heat rejection is lower for the first case. Your available energy or maximum work output will be more. It will be more efficient. That's the engineering. That's basically a engineering concept. I hope this is pretty much clear. This case was very, very important case. So you are supplying the same amount of heat and variable heat is rejected. Same amount of heat is supplied and variable heat is rejected. So if you reduce the heat rejection, your efficiency will increase. So for the first case, when the power plant is operating between a temperature limit of T1 and T naught, so heat supplied is Q1, that is T1 delta S1. And in another scenario, for other case, other plant, Q2, which is with heat supplied should be same as initial Q1, it will be T2 delta S2. But T2 is less than T1 or T1 is greater than T2. So to maintain the product T delta S, your entropy should be greater. That means your entropy of 2 is greater than entropy of 1. So that means if you go make a graph of T delta S, your heat rejection, that is Q naught, is T naught delta S1 for Q1 and T naught delta S2 for Q2. And since delta S2 is greater than delta S1, so T naught delta product of T naught delta S2 is greater than T naught delta S1. That means heat rejected for second case is larger than heat rejected for first case. So that means your efficiency is 1 minus Q rejected by Q supplied. If Q rejected is higher, then efficiency is lower. Second case has a lesser efficiency compared to the first case. So first power plant is much efficient. And efficiency is work maximum by Q supplied. So Q supplied is same for both the cases. So that means your work maximum for second case is less than the work maximum for first case. And work maximum is nothing but your available energy. So available energy for the second case is less than available energy for the first case. That means you have more amount of unavailable energy, which you don't want in the second scenario. And that we will calculate. That is increase in the unavailable energy from the first case. So increase in unavailable energy will be the difference of delta S2 minus delta S1 for the heat rejection. Unavailable energy is basically heat rejected to the sink, minimum possible heat rejection. So in the second case, it was T naught delta S2. In the first case, it is T naught delta S1. T naught take common out. T naught delta S2 minus S1 is your increase in the unavailable energy. That is evident from the graph also, highlighted in red. Okay. Now, what is delta S1? So it is Q1 by T1 and delta S2 is Q2 by T2. So if you put them, it's T naught Q2 by T2 minus Q1 by T1. Since Q1 and Q2 are equal, Q1 comes out. And this is the increase in the unavailable energy. So in whole, we can summarize that you should always apply heat at a higher temperature, always reject the heat at a lower temperature. Okay. Reduce the amount of heat rejection, increase the amount of heat for a same amount of heat supply. Okay. You should not burn your fuel. These are your fossil fuels. You cannot waste the resources. So engineering is nothing but for within a limited amount of resources, how you can get a maximum or optimized amount of work. All right. Is it clear? Two concepts, very, very important. So we can write a note here. Greater temperature difference, more will be loss of available energy. Greater the temperature difference, between T1 and T2, I'm saying. Higher the difference between T1 and T2, there will be more loss in the available energy. More will be loss. And same heat is having more importance at higher temperature. Therefore, same heat is having more importance at higher temperature. Okay. Think on it. Take a few minutes to grasp, and then we'll start back. Okay. I know that it's difficult to grasp sometimes this concept. It's a very heavy concept. I'll be back in a few minutes. All right. Let's come to the next concept of availability, right? Availability. So availability is basically maximum useful work in which systems comes into equilibrium with surrounding in a process. Okay, in which system come to equilibrium with surrounding for a process. So availability is defined for a process, whereas available energy is defined for a cycle. Okay, both are maximum possible work you are obtaining, but this is for a process. Availability is for a process. Available energy is for a cycle. So maximum useful work in which system comes into equilibrium with surrounding in a process. Okay, so it's a maximum useful work defined for a system, for a process. Okay. So suppose that means you have two states. You have initial state, you have final state. Okay, you have initial state and a final state. So this is your initial state. This is your final state. Okay. The initial state has some parameters, that is P1, temperature, volume, enthalpy, entropy, internal energy. So that is E1, V1, T1, S1, H1, U1. Okay. Whereas final state has different names. Final state can be called as final state. First name is final state. Another name is datum. Another name is dead state. Another name is atmospheric state. Another name is surrounding state. Another name is ambient state. And another name is reference level. So all of these names are for final state. Okay? Any of the name, and these have the properties. That is, so a process is going from this to this, and these are the properties: P naught, V naught, T naught, S naught, H naught. Okay. Now there will be again two cases will be defined because it's a process. There is a system which, so in that system also you are dealing with a process. So two systems are of how much type? Two types: closed system and open system. Okay. So for case one, for closed system, closed system. So when you're dealing with a closed system, so you know the TDS equation. TDS is du plus useful work. For a closed system, you write PdV eventually. Okay. So that is a useful work. That is your availability for a closed system. Maximum useful work you want to obtain. Okay. So let me draw again the graph. So this is your final state at T naught, P naught, P naught, S naught, U naught, H naught, and this is state initial state, that is T1, V1, P1, S1, H1, U1. There is one process from 1 to 2. There is a process from 1 to 2. That is this. And there's another process. Suppose at temperature T2, V2, P2, S2, H2, U2. And that is from this. This is a process. Okay. So one process is from T1 to T0, another process is from state 2 to state 0. Okay. So your TDS is du plus useful work, okay, in a closed system, CS, closed system. So useful work for a closed system can be written as TDS du minus TDS minus 1, TDS minus du. So what can be TDS? That is T into final state minus initial state minus U final state minus U initial state. Okay. All right. Clear. So when you are dealing with between state 1 and state 0, so what is final for state 0? So T is, what should be the T? You tell me. For a maximum useful work, what can be the T? You know that we want it to be as low as possible. Okay, till the dead state. Okay, so T should be T0, not T1. It should not be T1. It should be T0. Okay, so that is T0. S final is how much? S0, and S initial is 1. U final is how much? U0 minus U. Okay. So if you see S0 is less than S1, entropy at not position is less than, dead position is less than this position. So that is, this is a negative value eventually. So if you can also write like this, taking the negative sign common. So this can be written as U1 minus U0 minus T0 into S0 S1 minus S0. Okay. And that is your useful work of closed system between state 1 and state 0. And it should be T0. Why? For maximum work taken till dead state. For maximum reversible work. So take till dead state. So less is this value, more is this value. Okay. Okay. And if I say between state 1 and state 2, earlier I was taking from state 1 to state 0. If I say state 1 and state 2, that can also be a possibility between state 1 and state 2. Okay. So if you go for state 1 and state 2, useful work of closed system will be U1 is the initial state, U2 is the final state, T, what will be T? T will be T0 always. It should always be T0 for maximum scenarios. S1 minus S2. Okay. S1 minus S, not T1 or T2. It should always be T0. You should always take it to the ambient, okay, to get the maximum useful work. We can also prove this mathematically. Physically, you explain that you should always take T0, but let's prove it mathematically. Let's prove. Proof. From state 1 to 2, or 1 to 0. Let me write here state 0. Okay. So from state 1 to 0, useful work of closed system is U1 minus U0 minus T naught S1 minus S naught. Okay. For state 2 to naught, useful work is U2 minus U naught minus T naught S2 minus S naught. Okay. So if you subtract both of them, so from 1 to 2, subtract above, that will be useful work for that closed system is U1 minus U naught minus U2 minus U naught minus T naught into S1 minus S naught minus of minus, that is plus. So minus of minus is plus, that is plus T naught into S2 minus S naught. Is it plus? Okay. So this U naught and U naught cancels out. So that is U1 minus U2. And T naughts again comes out, same. So minus T naught, minus T naught into S1, and S naught and S naught cancels out, minus S2. So again, T naught is there. It's not T1 or T2. So that is your useful work for a closed system from the reference. Hence proved, you can say that. And that is the idle work. So you can say, therefore, useful work is for a closed system is defined as U initial minus U final minus T naught times S initial minus S final from the datum set. Okay. It should be less as possible. T naught should be lesser value so that this difference is higher, so that you get a maximum amount of useful work. And that is your availability. Okay. Okay. All right. Clear. So for a closed system, useful work is this. This is your useful work. And maximum useful work is availability. So to get maximum value, how can we get? So this is useful work, and maximum useful work will be the actual work which you are obtaining. That can you extract from a system. So maximum useful work that is your availability. And it is an actual work that can be extracted from the system. And this will always be less than the useful work for the closed system. Okay. It is actual work extracted from the system that can be extracted from the system. Okay. And it will always be less than the useful work. So what is maximum useful work? It is U1 minus U naught minus T naught S1 minus S naught. Also PDV will also come because atmospheric resistance is there in a closed system. Okay. And we have studied this. So maximum useful work of a closed system is nothing but, if you are going from state 1 to state naught, U1 minus U naught minus T naught S1 minus S naught. You're dealing between state 1 and state naught. Also minus PD for a closed system. That is your P initial. So this line is same, minus P naught. Again, we are dealing with the datum. We want this to be maximum. So P naught should be selected. V final minus V initial. That is V1 minus V naught. V1 minus V naught. So you can say it as U1 minus U naught minus T naught into S1 minus S naught minus P naught into V1 minus, sorry, V naught, it should be final minus PdV is final minus initial, that is V naught minus V1, because final is V naught, and if you take out a plus sign, so it will be V1 minus V, okay, with a plus sign. So you can write maximum useful work as, therefore, maximum useful work of a closed system can be written as U initial minus U final minus T naught into S initial minus S final plus P naught into V initial minus V final. All right. Because air resistance is always there for a closed system, that will play a role. Atmospheric resistance is there. Okay. That's why we have subtracted that atmospheric resistance work, because it's opposite to the work which you are doing. That's why you have to subtract from the useful work. And that is your maximum possible useful work for the system. And this is the expression for the maximum useful work for a closed system. All right. So for the closed system, we understood. Now let's come to the open system. Open system. Open system. Case 2. Open system. So here, open system useful work will be coming from enthalpy concept, because you know that equation TdS dH minus VdP. Okay, and VdP is your open system useful work. Okay, so you can write useful work of open system. Okay, the useful work of open system can be written as an enthalpy change minus the entropy change. So directly I'm writing the expression useful work of open system is Hi minus H final. Instead of Si, earlier we were writing Ui minus Um, it will be Hi minus Hf. Hi minus Hf minus T naught into Si minus Sf. Okay, this is a useful work. And what will be maximum useful work? Maximum, or that is your availability of an open system, is Hi minus Hf minus T naught into Si minus Sf. So there is no P naught into Vi minus Vi. Why? Because it's an open system and there is a control volume. So there is no resistance of the atmosphere. Open system is there. Atmosphere resistance is from everywhere. It's balanced out. It gets subtracted off from everywhere. Okay. So there is no atmospheric resistance. That's why it's same. So both are same expression for useful work. So expression of useful work for open system and maximum useful work for the open system is same. Let's write the note here. Expression of useful work of open system and maximum useful work of open system is same. Okay. So now we have understood what does concept of useful work or maximum useful work, or you can say it as an availability. Okay. Now we come to the concept of irreversibility. So irreversibility is the difference between maximum work and the actual work. Maximum work and the actual work. So useful work was your maximum work and actual work was your maximum useful work. Okay, you have to understand, don't get confused. Let me write irreversibility. It is difference between maximum work and actual work. I'll write here maximum work is useful work. Okay, and actual work is maximum useful work, or you can say availability. Therefore, irreversibility is work maximum, work actual. So this is work maximum, work actual, work maximum minus work actual. Because you have seen that useful work is higher than the maximum useful work. Okay, because of the atmospheric waste in case of closed system. Right? In open system, both are same. Okay, so there is no irreversibility. Irreversibility is zero if you say for an open system. Can you say that? You can say that. But doesn't mean that it is irreversible. It's irreversibility. Okay, these are two different definitions. Irreversible scenario is something different. You cannot take the same path. Irreversibility is different scenario, different meaning. Okay, the maximum work is always reversible or usable. Okay, availability is the maximum useful work in a system you can obtain, or you can write it as reversible. Okay, irreversibility is work maximum minus work actual. And there is a theorem by Gauss-Tudola which state that rate of irreversibility, this is irreversibility, and the rate of the irreversibility is directly proportional to the rate of entropy generation. Okay, let me write Gauss-Tudola theorem. Tudola states that according to this theorem, rate of irreversibility, earlier we understood irreversibility, now rate of irreversibility is directly proportional to rate of entropy generation. Okay, so you can say that irreversibility rate I dot is proportional to entropy generation ds dot. So it can be written as irreversibility dot s E naught into ds dot of universe, and universe is comprised of system itself. So it is T naught of ds of system plus ds dot of surround. That is your, I can write irreversibility I here, and this is I dot. Okay, so if you see, we did one question also. There one scenario where there were mixing of two fluids. Okay, So where we calculate the irreversibility, okay, change in the entropy. We have calculated that. Okay. Any doubts still here? Pretty simple. We understood available energy. We have understood unavailable energy. We have understood the concept how to provide the heat at a higher temperature, reject at lower temperature. We have understood the concept of availability, where there is a concept of useful work and a maximum useful work. And irreversibility is for both closed system and open system. And irreversibility is basically the difference of maximum work minus the actual work, where maximum work is reversible work or useful work, and actual work is availability, maximum useful work. All right, any doubts? So take a minute. I'll be just back in a few minutes. All right. Now let's come to the concept of Gibbs function. Gibbs function and Gibbs-Helmholtz function. Gibbs function. So what is a Gibbs function? It's basically a difference of enthalpy and Ts. So it basically represents the open system work scenario. Open system work scenario. So Gibbs function G can be written as difference of H minus Ts. How? It represents Open system work. So what is an open system work? TDS is equal to DH minus VDP. Okay. And this is a work done of open system. So this is work of open system. So work of open system is DH minus TDS. So it's same as on log E. So this is G is equal to H minus TS. Okay, cool. Analogous. So we know that G is equal to H minus TS. So take our differentiation. So dG dH minus d of TS. That can be written as dH minus TDS minus SDT. And what is dH minus TDS? That is open system work. VDP. VDP minus SDT. So dG is VDP minus SDT, or you can say that G is equal to Gibbs function is difference of H minus TS. VDP minus SDT and H minus TS. All right. So this is a Gibbs function. It represents an open system. Whereas Gibbs-Helmholtz function is represents the closed system. Gibbs-Helmholtz. So this is Gibbs function. Helmholtz. That is your H. Oh, sorry, F. What I'm writing. H is enthalpy. F. Denoted by F. So F is U minus TS. Open. It represents closed system. So F is U minus TS. So it represents closed system work. Okay. So what is closed system work? Equation TDS is equal to du plus PdV, and that is your work of closed system. So work of closed system is du minus TDS. That is nothing but F is equal to U minus TS. Okay. Now differentiate dF du minus d of TS du minus TDS minus SDT. So what is du minus TDS? That is your PdV, your closed system work, minus of PdV, right? So du minus, since du is TDS is du plus PdV, so it is minus of PdV minus SDT. That is your TF. All right. Yeah. So this is your Gibbs-Helmholtz function. Now we have studied what is PMM1, which violates the first law of thermodynamics. What is PMM2? So PMM2 is a perpetual motion machine of second kind, and it states that it's impossible machine because it violates second law of thermodynamics. That is, complete conversion of heat into work is not possible. Okay. And if you put petrol in a, suppose take an example of a bike. If you petrol and without the exhaust, you are getting whole amount converted into work. You're getting as bike is running without even exhausting anything out. That's not possible. So that is a perpetual motion machine of second kind. EMM2. It is impossible because it violates, sorry, not violates, violates Second law of thermodynamics. That is complete conversion of heat into work is not possible. Okay. What is PMM3? So it is a perpetual machine of third kind. It is impossible to construct a device which runs completely in absence of friction. So it's near to the third law of thermodynamics, violating the third law. Okay, so PMM3, and I'll tell what is third law as well. So impossible to construct a device which runs completely in absence of friction. Okay, because in real and scenarios, friction will always be there. And what is third law of thermodynamics? It is impossible to achieve absolute zero temperature in a finite number of processes. Within a finite number of processes, you cannot achieve a zero absolute temperature. Okay. Or there is a statement which came out from here was Nurse Simon's statement. It states that entropy of a pure crystalline substance is zero at absolute zero temperature. Okay. There is no randomness even at a molecular level. Okay. So what is third law? It is impossible to achieve absolute zero temperature in a finite number of processes. In a finite. Okay. And from here, a statement came. No Simon statement, which states that entropy of a pure substance is zero at absolute zero temperature. Okay. Now there is a short concept of compressibility factor. So compressibility factor represents deviation of a real gas from the ideal gas. Okay. Compressibility factor represented by Z, capital Z. It represents deviation of real gas behavior from ideal gas behavior. Okay. And mathematically it is represented as Z is equal to PV by RT. Okay. And if Z is 1, there are three scenarios. If it is less than 1 or greater than 1, it is a real gas. But if it is equal to 1, it is ideal gas. PV is equal to RT. Then Z is 1, PV is equal to RT. Ideal gas. Okay. And what is the concept of reduced parameter? Okay. So it is defined as the ratio of actual pressure to the critical pressure. You will see these terms. Reduced parameters are written somewhere. It is defined as ratio of actual pressure to critical pressure, or actual parameters to critical parameters. Critical parameters. That is, if you write pressure, reduced pressure, it is P by P critical, or you say reduced temperature T by T critical, or you say V reduced is V by V critical. Okay. There is one concept which comes, we say second law of efficiency. That means you are dealing with losses. Okay. So second law of efficiency or second law of COP word you will see. So it is second law efficiency. So it is nothing but in terms of concept of our producing devices, it is actual to that of reversible or maximum, or in terms of work absorbing devices, it is COP, coefficient of performance of actual, to that of COP of reversible. Okay, pretty simple. All right, I think let's keep it till here for this session. I hope there are no doubts. We have discussed a lot in today's session. So I expect that you all are regular with your lecture videos by the prof on NPTEL portal, and those who have missed the sessions, they can watch these tutorial sessions, and all of the tutorial sessions are uploaded on my YouTube channel. Okay, so I'll write the YouTube channel name. So my YouTube channel is NPTEL with Varnit. So those who have enrolled in the NPTEL this thermodynamics course, you eventually get a sheet on the portal, from the portal or from the mail as well, where the links of all the recordings are there, as well as the link of the Google Drive where all the notes are there uploaded. Whereas those who are watching this video for the first time on the YouTube channel, so all of these PDF notes are available in the video description. There's a link, Google Drive link. You can open up and you can check out for each week tutorial. So, all right. So I'll see you guys in the next class, next tutorial, next week, next Tuesday. Till then, bye-bye.